neutrons, electrons. We also talk about the locations. Protons and neutrons are found in the nucleus, and electrons are found in electron clouds. But when we do the electron configurations, we actually put electron shells. We learned about the naturally occurring elements. We talked about hydrogen, carbon, nitrogen, oxygen, sulfur, phosphorus, which I wrote in my last notes. And those are basically what make up most of the living world. We learned how to read a periodic table. So in the periodic table, it gives you a lot of information. It gives you the abbreviation of the name. So for example, carbon, the abbreviation is C, nitrogen is N, oxygen is O, but something like sodium is not S because that is the abbreviation for sulfur. So for sodium, it would be Na. So it just depends what kind of root does it have for the abbreviation. We learned that there's an atomic number that tells you the number of protons. And we also learned that there's an atomic mass. And with that information, you get the number of protons plus neutrons. And you also know that if you know the number of protons, you also know the number of electrons. We also learned how to determine how do I make the electron configuration for different elements. Like I could do it for carbon, I could do it for nitrogen, and so on. And also we learned that based on the shells, so I could do the shell, put the placement of the electrons on these electron shells. And so for example, here's a picture, and you could tell like lithium, for example, it has 3 protons, therefore it has 3 electrons. So what you see in this picture, you see that 3 electrons placement. So we learned that there's rules. So for the first electron shell, you could only put 2 electrons. So for lithium, for example, because it has 3, then it has to jump to the next electron, to the next shell. So you would put the extra electron there. So in this case, carbon, on the other hand, has 6. 2 go on the first shell, and then they jump to the second shell, the remaining 4. So because carbon and lithium and boron and nitrogen and oxygen, if you look the number of electrons on the outer shell, notice that it doesn't have the maximum number. In this case, the maximum number of electrons on the second shell would be 8. But for example, oxygen, you only see 2, 4, 5, 6. So it's missing 2 electrons, therefore it's reactive. So as opposed to neon, on the other hand, you look, the number of electrons on the outer shell is a total of 8. So neon would be considered to be stable, and it kind of makes sense because it's a noble gas. Therefore, it doesn't bond with anything else because it doesn't have to. So this is, you could see a placement on how these electrons are placed, and you could determine if it's reactive or not. And that's what we basically, where we left off in our last class meeting. We talked about atomic number, atomic mass, and if you have a piece of information, you could, from there, calculate the number of protons, neutrons, and electrons. Okay, so now we talked about if it's reactive or stable. So we also talked about that. And also we learned that only the electrons are the only ones that they bond with other molecules. And also we also learned that the further you are from the nucleus, the more energy those electrons have. So those are the electrons that make bonds with other molecules. So later in the chapter, we're going to learn about type of bonds and how do these elements make bonds with other elements, and so on. Okay, so now there's a concept. These are called, what is an isotope by definition. So when we think of isotopes, isotopes have the same number of protons and behave identical in chemical reactions, but the difference of an isotope is if they vary away from if the number of neutrons changes. So by definitions, so isotopes have the same number of protons, but the difference is in the number of neutrons. So here's an example of different isotopes. So for example, you have carbon 12. So carbon 12, if you break it down into the subatomic particles, what you're going to see is that carbon 12 has 6 protons, 6 neutrons, and 6 electrons. Okay, so how is that different from carbon 13 and carbon 14? So if you notice, the number of protons and electrons have not changed. So they still have 6 protons and 6 electrons, but what has changed is the number of neutrons. So for example, so protons remains the same for carbon 12, 13, and 14. And what you see now is that in this case, the number of neutrons has changed. So for carbon 13 is 7 and carbon 14 is 8. So because the number of neutrons have changed, then you consider carbon 13 and 14 to be isotopes. Now, sometimes we refer to radioactive isotopes, which is one in which the nucleus decays spontaneously. So those are reactive. So those are not all isotopes are reactive. Okay, so here's an example of how an isotope is used. Specifically, a radioactive isotope is used to treat prostate cancer with radiation. So for example, among American men, prostate cancer is the most frequently diagnosed cancer. And one of the treatments, of course, there's more than one way to treat cancer, but one of the treatments for prostate cancer is using either surgery and also radiation. So studies of the effectiveness of different methods such as surgery or external radiation sometimes create issues because sometimes it's not as, because some groups of patients are not controlled for all characteristics of how the treatments are slightly different for different patients. So sometimes they put these radioactive seeds, for example, like if you see in that picture, can be inserted in the tumor, and they will keep track of, like, if they'll put it with the medication and compare and see if the treatment is working or if the medication is working or not. So sometimes they could be used for different treatments by using these radioactive isotopes. Now, sometimes when we represent molecules, there's more than one way to represent a molecule. So sometimes and remember, we go back and define what a molecule is, and I'm just gonna go and project the definition so we could just go back and refer. So if you go back to a few slides, I think it's later on, we defined the term, what a molecule is. Go back. I like to just point out exactly where it is within the lecture. Please just give me 1 second. So if we look at different molecules, right? So in this specific example, we're looking at formaldehyde. So now you in the comment, so you would write the name, and you would write the formula that represents formaldehyde. So this is kind of like a fancy molecule, right? But then you could look at the same thing as like water, like H2O. So we could refer to the same thing as like water or methane or many different molecules. Okay, so now there's many different ways to represent molecules. We could do the electron configuration to represent a specific molecule. In this case, we're looking at something like this. It tells you the placement of the electrons and the bonds between how you connect in case of water, where oxygen connects to the hydrogen, and how many electrons are shared between the bonds that you make that specific molecule. That is an option, right? Another option is, so that would be like if you want to do the electron configuration. So that would be looking at this format right here. Or you could represent the molecule by looking at the structural formula. So the structural formula would be, it tells you the placement of a little bit of like the geometry of the molecule, but also it tells you the number of bonds that you make between carbon and oxygen in this case, and carbon and hydrogen. So for example, here you see that if you see one line like here, that tells you that 2 electrons are being shared between carbon and the hydrogen. So if you see 2 lines where, like for example, single bond versus double bond, a double bond tells you that you have 4 electrons are being shared between carbon and oxygen. So that kind of tells you like the lines, they represent something. So again, we'll talk a little bit more about that. So we'll see like if it has a single line, that's a single bond, and that means 2 electrons are being shared. If you have 2 lines, that's 4 electrons are being shared between the 2 molecules. And if you see 3 lines, that means that would be a triple bond, and that means that how many electrons are being shared between those 2 molecules. So that would be a structural formula. Sometimes you could do a space field model, like you see in this picture right here. So that space field model would be kind of gives you perspective of size. So for example, oxygen and carbon and the hydrogens. So that would be another way to represent the same molecule. And sometimes we have kits where you do like a ball stick model, and it tells you like how you would rearrange if you have carbon, oxygen, and hydrogen. It can also give you a perspective of size too. So you could see the representation. That would be carbon, that would be oxygen, and these 2 would be your hydrogen molecules. Okay, so now let's talk about chemical bonds. Okay, so what is a chemical bond? So we're just going to go by simple definition. So when we see a chemical bond would be an attraction between 2 atoms. And because of this attraction of 2 different atoms, you either going to end up either sharing electrons. So you're either going to share electrons, or sometimes you end up transferring electrons. And because depending on how these molecules are interacting with one another, then you would determine the type of bond that these molecules are making. So not all bonds are going to be the same. And also we also going to learn that within the different types of bonds, some bonds made are going to be weak and some bonds are going to be pretty strong. So we're going to go over and talk about the different types of bonds. So for now, we're going to see that we're going to go over types of bonds that they're weak and examples of bonds that we're going to make. They're called hydrogen bonds. And we're going to go over and explain how you make hydrogen bonds. And we're going to talk about ionic bonds also. And we also going to talk about strong bonds. And examples of strong bonds are going to be covalent bonds. Okay, so let's start with the, so let's go back, understanding what a bond is. So a bond is an attraction between two atoms resulting from either sharing of outer share electrons or the presence of opposite charges between atoms. And then, again, we're going to talk about different types of bonds. We're going to talk about hydrogen bonds, ionic bonds, covalent bonds. And we determined that hydrogen and ionic bonds, they happen to be weak bonds. And we're going to also talk about strong bonds. In this case, are covalent bonds. Okay, so let's start with ionic bonds. So first of all, these bonds, they're weak. These are weak bonds. Okay, so by definition, what is an ionic bond? So ionic bonds, you're gonna have an atom, that specific atom is gonna either lose or gain electrons. And when that event happened of either gaining or losing an electrons, that specific atom is gonna end up with a charge. So it either ends up with a positive charge. So if it has a positive charge, it's called a cation. And if it ends up with a negative charge, an anion. Okay, so ions are atoms or molecules that are electrically charged as a result of either gaining or losing electrons. And right now I'm just defining, I'm not showing you any examples, but I will. So when that happens, when you either lose an electron or gain an electron, because now you have a charge, then that charge is going to form a bond, and that bond is called an ionic bond. Examples of ionic bonds include like table salt, and these are held together by ionic bonds, and they're called ionic compounds. So let's look exactly how this happens. So once you see it, it's going to make a lot of sense, and we'll go back to definition. Okay, so let's look at salt, because this is a classic example of how ionic bonds are formed. Okay, so let's go back. So if I look at the periodic table and I find sodium, so this is sodium right here, and the abbreviation for sodium is Na. So if you look at the periodic table, just give me 1 second. We'll go back to a few more slides and see the periodic table and find sodium and chlorine. Give me 1 second. Okay, so you're gonna go back, and I'm just gonna find, I know this takes a while, but I'm gonna go back and I'm gonna find those two molecules. And I'm gonna go over, because I want you to pay attention to two things. Okay, so here's sodium, and then Cl, sodium chloride, and I'm comparing sodium and chlorine. Okay, so I'm comparing sodium and chlorine. So notice that the atomic number for sodium is 11, and the atomic number for chlorine is 17. Okay, so that's the atomic number. So that tells me the number of protons that sodium has and the number of protons that chlorine has. And of course, it also gives you the atomic mass, which is, that would be this number here on the top, right? So that would be the atomic mass. So that's the information that I get from there. So another look at the colors. So we are looking at, in this case, like we're looking at chlorine and based